I'll start from the very beginning. Although Ruba asked me to start from the regression correlation part, but I decided that I'll just start from the very beginning because there are certain concepts that are very confusing at times for you people. And when you actually apply them, it's necessary that you understand exactly what you are trying to do and what you want to do. When we do statistics, we do a lot of mathematics, but then I'll try and discard all the mathematics. You don't need that, okay? But there would be some symbols, maybe I'll explain them to you as I go along, but you can ignore them if you feel like, okay? Just try and understand the concepts, okay? Because ultimately, these days, you'll not be working with a calculator, you'll rather be working with a computer, and the computer does everything for you almost. So one good thing about it is, okay, you don't have to really bother about calculating things, but the other thing is that what should be your input and what should be your output. Okay, so it's important that you actually give the computer the correct information. And then when the computer returns whatever it does, the results, okay, you need to interpret them properly. To do that, you need to understand what you are doing, basically. Okay, so that is one thing that I have found that very often you're not quite aware of. You get an output and then you're not sure what the output tells you. Okay, so that's the reason I wanted to talk to you about from the very basic statistics, so that you have a clear understanding of what exactly you want to do and what exactly the results tell you. Okay, so I'll share the screen with you here, my presentation, and if necessary, I've got a blackboard at the back of me here, so I'd go to the blackboard at times if necessary. Okay. Can you see this, every one of you? Is this visible to all of you?
Yes, sir, it is visible.
Okay, fine. So we'll be talking about descriptive statistics as such. And to begin with, what is statistics and why do you need to do statistics? Okay. As I said, statistics involves a lot of mathematics, but it is not mathematics per se, because mathematics can sustain itself on its own. Okay? You don't need any other science for mathematics to sustain itself. Okay? But then statistics requires other science because it requires data. And without data, you don't have statistics. So it's more about data analysis. So in a narrow sense, we can say that statistics is about collection, compilation, and analysis of data. Okay? This last part, we'll just put it in a broader sense. Analysis of data actually means that we want to make meaningful statements about an experiment or phenomena. Okay? So we do an experiment, whatever the experiment is, we collect data from the experiment, and then we want to make certain statements. Okay, very simple examples would be the students in a class, and I want to find out the average height of the students, the salary of all individuals living in Calcutta. Okay, so if you are looking at the current pandemic, then the proportion of cases among the people. So there can be different types of statements that we would want to make based on some experiments. So these are different experiments that we'll carry out and different types of statements that you'll be making based on it. So the primary goal of statistics is to use a given data to infer about a larger aspect that the data relates to, and this I'll explain in greater details. Okay, but before that, let me come to what is meant by experiment. By experiment, we mean any phenomena that we intend or are interested to study. Okay, it's not necessarily, whenever we talk about experiment, we have a feeling that we are in a lab doing some, okay, mixing chemicals and things like that. No, it's not that. Experiment can be studying any phenomenon. Okay, so just maybe looking at the sky and counting the number of stars there in a particular area of the sky, etc. Those can be experiments as well. So what he will be primarily uh, involved with would be things like social sciences, health sciences, etc. Well, you go out to collect data on the food habits of people. So these are experiments as well. Okay. So it's the focus of our study, basically what we want to study. It can be the heights of adult women, number of matches won by a football team, the number of patients cured by a given medicine, length of remaining life of a cancer patient, increase or decrease in the pollution level. So there can be a host of experiments that we can think of. Okay? And when we talk about experiments and what is the focus of this experiment? So the focus of an experiment is the population. So the population is used in everyday life. We just use the word to mean a group of people. Okay. So it's a totality of all individuals or units that we intend to study. Okay. So that is the focus group. Okay. Very often, this it can be very large, it can be hypothetical, it can be experimentally destructive. What do I mean by all these? Usually, suppose, let me give you an example. I want to find out the average, and this is something everyone talks about, per capita income of Indians. Now, what does the per capita, so per head income of Indians. So what is the population in this case? I'm trying to look at all the Indians. Okay, so it's 1.3 billion Indians, that is my population. Okay. Instead, if I'm looking at, say, just the per capita income of people in West Bengal, so Bengalis, then I'll just be restricting myself to the state of Bengal, and the population would be all those living in Bengal. So you need to define the population first. Okay, so it's always, why do I say it can be hypothetical or experimentally destructive? Okay, let me come to the hypothetical. Okay, every one of you have tossed a coin, right? And what is the probability or chance of head? You say that it's half the time it's going to be head, half the time it's going to be tail. How do I know? We generally don't. Okay, so you assume that it's half the time head, half the time tail. But it can be that the coin is weighted on one side. So there may be one side is heavier than the other, so the heavier side will always fall below and the lighter side would come up. Okay, so it might be that this coin, we call it a biased coin. It's unbiased if it has equal chances. So it might be it's a biased coin. Now, if I have a biased coin, how do I know what is the probability of head? So usually with an unbiased coin, if I have a normal coin, how do you find this out? Can you tell me whether the coin is normal or not? How do I find that out? Any guess? Okay, what you can do is you can toss it 10 times, and if 5 times it comes out head and 5 times it comes out tail, you will say that, okay, the chance is equal. But then in 10 tosses, there may be some variations. Okay, all of you have played Ludo, for instance. Okay, and the 6 comes out, it should come out every 6th time, but it doesn't actually. Okay, so there are certain chance factors. So it might be, if I make the sample a little larger, instead of looking at 10, if I look at 50, then probably it will come to very close to 25 each, and then I can say that they are equal. Okay? But how far can I go? In fact, you can see that you can just go on tossing the coin infinite number of times. Okay, but that is not possible. So the population in this case, the number of coin tosses can be infinitely large. Okay, so you can keep on doing this day after day, etc. So we can't go up to that. So we say that the population in this case is hypothetical. There is a very large population which we actually cannot measure. Okay, I'll come to those problems in a moment, how we can do that. Lastly, it can be experimentally destructive. It's something like uh, a company makes electric bulbs, okay, and the bulbs are good. You'll buy the bulbs if, say, a retailer is buying the bulbs, okay. So they make it in batches of, say, 500 bulbs. So one lot of 500 bulbs. How do I know that this lot is good? The lot is good if a bulb actually works for 200 hours. Okay, you light it on, it is working for 200 hours, it's good. If it goes off before that, then the bulb is not good. Suppose we decide on this. Then what do? You have a batch of 500 bulbs and you want to find out if the bulbs are good. What did you do? You switch on all 500 bulbs? Yes? Yes or no? You do that? You can answer me. Yes. Oh, don't be shy to answer me. Okay, it's fine. Can you do it or can you do not? Can you not?
Microphone tap.
No, no, sir. We can't. We can't do that.
Can you do that?
No, sir.
Oh, why not?
Because it will destroy all the.
Yes. So basically, you'll have nothing to sell after that, right? So you
Yes, sir.
cannot, it can be experimentally destructive. So sometimes the population, when you study this, when you do the experiment, it can be destructive and we don't have anything left if we use up everything. Okay? So population is usually large, it can be hypothetical, it can be experimentally destructive, but I'll come to that. But any characteristic of a population is called its parameter. I'll be using this term, and in fact in your next classes also you'll be using the term parameter. Parameter is like, if I'm looking at all adult Indians, the parameter may be their per capita income. What is the average income of Indians? That is a population characteristic. That is the average income of 1.3 billion Indians. Okay. So you know something about mean. Okay, I'll come to mean anyway. So that can be we call it the parameter because it characterizes the population. Okay. Then the population may be all persons with weights greater than 100 kgs, and you're looking at this so you're looking at obese people, and the parameter may be probability of a cardiac arrest. So what proportion of heavy or obese people have a chance of cardiac arrest? The probability of that would be your parameter. Okay, so the population is weight is greater than 100 kgs and the parameter is probability of cardiac arrest. Now, as I said, the population is generally very large. So what do? You cannot really study the population. As you right now said that you cannot look at all the 500 electric bulbs because that will destroy the whole lot. Okay. You cannot be actually going around and asking 1.3 billion Indians as to what their income is. That's huge. That will take days and days, years in fact. Okay. So that is not possible. So how do I study the population? What I do is I take a part of the population, which is referred to as a sample. So sample is a part of the population that we actually observe and study. So whatever you do, you'll be doing experiments. In the experiment, you want to do a bigger thing, but then you'll have to collect data and you have a sample. Okay? Now, when you look at the sample, the data that we look at refers to the sample observations. Okay? And any characteristic of the sample is referred to as a statistic. So, sample is a small part of the population. Okay, it's just a part of the population. And any characteristic of this part of the population is referred to as statistics. I think sample is something that you are very familiar with because you have actually calculated, you have done a little bit of statistics, and most of it relates to the sample. Mind you, it doesn't relate to the population. Okay? So let me give you an example. We said that we want to find the average income of Indians, per capita income of Indians. So what we do instead, we select 1000 Indians and say that this is my sample. So out of 1.3 billion, we select 1000 Indians. So 1.3 billion is my population, 1000 is my sample collected from the population or selected from the population, and then we collect data from this 1000 individuals and do a mean of this. Take the average of this 1000 incomes. Okay, so this is not mind the average of 1.3 billion, is just the average of 1000 Indians. So these are two different things. And this average we call a statistic. So this is a characteristic of the sample, not of the population. The population was the average of the 1.3 billion incomes. Okay. Similarly, for the selection in the second case, I think I've got a mistake here. A selection of 100 individuals with weights greater than 100 kgs. We select 100 individuals from this. All individuals with weight 100 kgs. There can be a large number of individuals with weight more than 100 kgs. We just select 100 of them and look at how many of them have had a cardiac arrest. Okay, so the 100 in this case is my sample out of all possible individuals who have weight greater than 100 kgs, okay, or who are obese. I select 100 of them as a sample, and the proportion in this sample is what I observe. Okay, so now we have two parts to it. One is the population, the other is the sample. And then we come to what is referred to as statistical inference. And this is something you'll be doing in a later class. So where is the problem now in statistics? And this is the major part that we deal with in statistics, the inferential part. Okay? So we are interested, mind you, nobody is interested in this 1000 people who have selected. We want to talk about the average income of 1.3 billion Indians, not 1000 selected individuals. Okay, so we are interested in the population and want to take decisions on the population. However, it's too large. We can only study the samples. Population is too large to study, and we only got the results of the sample. So the data is the results of the sample. Okay, and what we need to do is we need to bridge the two. So statistical inference is about taking decisions or inferring about the population based on the sample. So you want to, I'll repeat this, you want to look at the sample, you want to look at the population. It's too big, you can't study it. You just take a part of the population, which is the sample, study the sample, and then try and get back to the population. Okay, somehow you have to relate the results that you get from the sample with the results with the what the population stands for. Okay, so that is what statistical inference is about. Okay? Now, as you can see that you can have good inference only if the sample closely resembles the population. Okay? Before I come to the next slide, okay, let me explain this a little bit. I talked about. Let me take another example, and suppose I'm looking at heights of Indian males, and I want to look at the average height of Indian males. How do I go about doing this? So there would be half the population. So it's half of 1.3 billion would be approximately males. Okay. So do I go and collect or measure all these individuals, some 6.5 million. Okay, so half of 1.3 billion would be a huge number to look at. So I can't go around measuring everybody. I collect a sample of, say, 2,000 individuals, males, and then measure their height, and then try to say something from this height to actual height of 1.3 divided by 2. That's the half of the population. That's the Indian males. Okay. In this case, suppose I pick up everybody from West Bengal. What happens? So my 2,000 sample comes from West Bengal only. I took the 2,000 Bengalis. I just picked them up, measure their heights, or maybe something somewhere from the northeast. I measure their height and try to say something about the population height. What would you expect? Okay, alternatively, I could have picked up 2,000 individuals from Punjab, Haryana. Okay, usually they're taller. Okay, so if I take their average height would be more than the actual height of Indians, whereas the heights of Bengalis or northeastern people there is usually lower than the average height of Indians. So if I take a bad sample, if I just take it from West Bengal, Northeast, or from Punjab, Haryana, etc., I get very far away from the actual value. Okay, so I cannot use this sample as a representative of the population. So it's important that I collect data from throughout India so that you have some people from Punjab as well as some people from Bengal. So some will be taller, some will be shorter, and on the average you'll come more closer to the actual average of the Indian male height overall. Okay, so you have to have a good sample which actually can be used to make inferences, good inferences about the population. So it's important that you have a reasonably good sample. This is something that we very often forget. We very often, when we do an experiment, very often we forget the goal of the experiment. So what exactly is what we want to look at, okay? And what exactly should our data be related to this? I'll give you examples that we come up with students here. For example, you want to do a psychological study. You want to see that just how much, maybe something like this. How much students spend on studies. Okay, how much time they spend on studies, how much time they spend on surfing the internet, for example. You're saying that how much time students, or maybe I'll put it more generally, how much time young people in the age group of, say, 18 to 25 spend on surfing the internet. Okay, I want to do a study for this. So my population is young people, maybe just in Calcutta, maybe. I'll just, young Calcuttans in the age group of 18 to 25, how much time do they spend on surfing the internet? Okay? Because I want to see how much time they spend on study, etc., etc. So am I going wrong at the very onset? Any idea? Is this right? If I want to find out how much time you want to spend on studies or how much distraction students have, am I wrong on this? Okay, I'll tell you why I'm right or wrong. Okay, but before that, so what do? I collect data. I can't go to all Calcuttans of that age group, so I collect the data. And say maybe I decide that I'll take 200 individuals and look at their patterns, how long they actually spend on surfing the internet on a particular day, etc. So I go around to the different colleges or maybe to the universities and collect the data from the students. And I collect data for 200 individuals and find the proportion. Suppose I see that about, say, 50% of them spend 3 hours or more on in surfing the internet. So what would be my conclusion? Can you guess what my conclusion is? Yes, you're free to guess on this. Any one of you? I have picked up 200 students and I've looked at the time they spend, and I've found that 50% of them spend more than 3 hours in surfing the internet. What would be my conclusion? That all Calcuttans in the age group of 18 to 25 do that? No, of course not,
Half of
because
them.
your sample, half of them. No, you see, you have got a problem here. Problem is, all Calcuttans in the age group of 20 to 18 to 25 do not attend college or school, college or university. There's some who have jobs, etc. Okay, so you see, the sample that you have collected is only from part of the population. The population we are talking about is 18 to 25 year age groups, Calcuttans of this age group. But many of them do not come to colleges or universities. Okay, so but the sample that you have picked up is only from this group. So the sample result would relate only to 18 to 25-year-old age group people in Calcutta who goes to colleges or universities. You see, the population is different. Okay? So very often we get confused with this. You have to be focused on this. If you are interested in all Calcuttans in this age group, then you have to collect data both from colleges, universities, and maybe outside as well, because there will be quite a lot who are working, etc. So you'll have to get data from them as well. So in that case, the sample will be different. It will be from a larger group. If you are collecting samples only from the colleges, universities, you can only say something about 18 to 25-year-olds who goes to an educational institution, not everybody. So you see the difference, So when you collect sample, you should be very careful as to what your focus of the study is. If the focus is the whole population in that age group in Calcutta, then you have to collect sample from all of them. Or you have to represent all the groups, not only those going to schools and or going to colleges or universities. Okay, that has to be correctly done. Otherwise, your inference will go wrong. You are collecting data from one part only. Okay, as I said, you are collecting data from West Bengal and trying to say everything about India. You cannot do that. Okay, if you want to say about India, then you have to collect it from different parts of India to make it meaningful. Okay, so it is very important to do proper statistical inference, but the first thing that you need to do is to collect the data properly in relation to the population that you have thought of. So first define what population you want to work with, and then you collect the data so that all the parts of the population are represented in your sample. Okay. Now, there are, I put it this way, the study of statistics can be divided into 4 major components. One is the study of the population. Okay, that is referred to as, okay, maybe I'll just keep to this. You have probability theory, probability distributions, related results. Some of this probably you'll be doing in the next class, little bit, not the mathematical part of it, but some ideas of this. Okay, so that is the study of the population. What are the characteristics of the population? How do I actually do it? That requires a lot of mathematics, studying the population as such. Okay. Then what you need to do is you need to look at the techniques of drawing a sample from a population. Okay, they now said that we can't study the whole population. I would require a sample from X. So how do I actually draw a sample from the population? Okay, so that has to be done in a proper manner so that I can go back and relate to the population again. Okay. Now there are 2 methods generally. One is experimental studies, uses what is referred to as design of experiments, and observational, sorry, I've got a spelling mistake here. Observational studies requires sample surveys. Okay. What is design of experiments? I'll give you because I'll not be dealing with these topics here. So I'll just give you a brief idea of what these are. Um, okay, let's look at a very current situation. Everybody is talking about vaccination for COVID. Okay, so new vaccines are coming up, etc. How do I know that a vaccine works? How do you do that? Any idea? They are doing this in the lab, okay? And they're saying that this vaccine is good for COVID. So how would you actually do this experimentation? Any idea?
By clinical trials
Anyone can
on
suggest?
several.
Yes, you are free to suggest. Okay, I'm asking you
Hello.
this.
Uh,
Yes, don't feel shy. Just ask. Just tell me what do you think
by
you'd be.
by conducting some clinical trials on several from animal to human beings.
Okay, we'll come to humans. Just we can skip animals. We'll look at humans.
Humans.
But how do you know that this is good enough? Suppose I've got a drug A. Call it a drug A. So how do you know the drug A is good for COVID? It's going to cure people who have COVID. So
We have to analyze it. Okay, sir.
I applied drug A to the individuals. Okay, suppose I pick up 100 individuals. I say I'll do the test on this 100 individuals. This 100 individuals, all of them are COVID positive. They have this just at the very initial stage, and I give them the medicine, and they get cured, etc. Okay, so some form of vaccination or medicine, and they get cured. Say, suppose 80% of them gets cured. Okay, so what did you say? That okay, this is good. 80% of them are getting cured. Okay, but as you know, that COVID is not a very fatal disease, right? It is very infectious, but not fatal, not very highly fatal like some other diseases. Okay? So if you do this experiment and tell me that, okay, 80% gets cured by this, so this must be a good vaccine or drug that you can use. My question would be, suppose I hadn't given them this, would they have been cured anyway? You would be able to answer me. Okay? So I have not tested this. You've just given everybody the drug. Okay? What you should have done probably is to divide these 100 individuals who have COVID positive into two groups. One group of 50, the other group of 50 again. Give one group of 50 this medicine and give the other group of 50 no medicine, just as before. Okay. And maybe you'll find out that if you don't give them the medicine, then probably out of 50, 42 survives. And if you give them the medicine, then out of 50, only 38 survives, a total of 80. What did you say now? You see, you haven't done the experiment properly because you have to do it against something, against a placebo. If you give somebody everything, everybody everything, then you don't know the difference. Okay? To bring out the difference, you'll have to give some of them the vaccination, some of them no vaccination, and then you can only judge whether the vaccine actually has an impact. Okay, this is, yes, you talked about clinical trials. This is what clinical trials would do. They divide this into two groups and then find out how it actually works for the two groups, what the results are from the two groups. If you don't have two groups, you cannot really say whether this is good or bad. It might have been that without giving this has a detrimental effect, and without giving this, you could have had 90% who would have been cured. Maybe because of giving the disease, some of them did not get cured. Okay, so that could be a problem. That could always be a problem because you have not designed the experiment properly. But then you have done it properly now. You have got two groups, you have done the experiment and come back to me with the experiments, etc. And I ask you another question. I ask you that there is a saying that older people are more affected by this disease than younger people. Okay, is it possible that the medicine that you have given is only to the younger people, and the medicine, the placebo group or the group that you have not given are the older group? If that happens, then what happens? Because they have the older groups anyway, those that doesn't have that group will generally have a higher fatality rate. Okay. So again, you have not done the experiment completely nicely. Okay, you can't answer all the questions from this. So what you have done, you should have probably divided this into 4 groups of 25 each. So for the first group, you give them the medicine, and this first group consists of young people only. The second group, again, you give them the medicine, but this comprises of older people, 65, 70 plus people. Third group, you do not give them the medicine. This group again comprises of young people only, but you do not give them medicine. And the fourth group is the older people who you do not give medicines now. Okay, so 4 compartments, and now you see what the fatality rate is in these compartments. Okay, and now you can answer both my questions. Okay, whether the drug is good enough and whether it is true that this fatality is higher among older group than among the younger group, and whether the drug can do better for this older group because there's higher fatality. The young are going to be cured anyway, so it doesn't really matter in that case. So you see, you have to plan the experiment properly before you can actually draw inferences from them. Yeah, and that is something that you should be careful of. There will be other questions, whether it's the same for males and females. So when you go for a drug test, okay, any experiment like this, you need to take everything into account, so that after you have done the experimentation generally is very costly. So after you have done the experimentation, you do not come back and see that you can't get all the answers. So you have to do the layout very, very carefully before doing the experiment. This is something we don't think of when you do an experiment. Okay? So this is for experimental studies, and the methods that we have for this are referred to as design of experiments. Okay? As opposed to this, we have what are referred to as observational studies, which are based on sample surveys. So in this case, you are not doing an experiment, and this is probably something that you'll be facing a lot. You just go out and collect the sample. But then, as I said before, when you collect the sample, it has to come from all parts of the population. Okay, there are various methods for doing this. Okay, I'll ask you something. I'll ask you that how do you collect a sample of, say, 2,000 Indians? How do you do that? Any guess? I want to look at the per capita income, or maybe the heights, etc., whatever. I want to get a sample of 2,000 Indians out of 1.3 billion Indians. How do I do that? You do a lottery and pick up 2,000? Yes? Okay, you can do that. You can do that, and if you do that, you may land up with everybody coming from the Maldives, from the Andaman Nicobars, or maybe from just West Bengal, or maybe just from Gujarat, etc. So all 2,000 comes from there, and you don't have the average Indians of the, or the average value for the Indians. Okay. So what else can you do? You can decide that, okay, I'll rather of this 2,000, I'll pick up, say, 100 from West Bengal, 150 from UP, this being a larger state, 80 from Punjab, some 50 odd from Gujarat, etc. So I'll divide this up for all the states. So I'll go state by state and collect data from all the states, so that the data is representative of the population. Okay. Sometimes this is very difficult to do, and there are various techniques that we use. Okay, some simpler ways of doing this, because you can't go to all the states, collect random collections of data would be very difficult to do it. But there are methods for this, and these are referred to as sample survey methods. So have you heard of the organization NSSO? NSSO is a very big, it's the National Sample Survey Office or organization, as they used to call it. Okay, it collects data on all India basis, and they collect data from every corner of India. Okay, and the majority of the results that you find out that comes out in the papers are actually collected by them. But they have a very good sample survey method to do that. Okay, so it's very important that you do this survey very carefully. If you are doing an experimental study, you have to do the design first. If you are doing an observational study, you have to define your sample survey method and collect the data accordingly. What for? Okay, what for I'll come to later, but once you have collected the data, then you study the data. And this is a study of the sample. We generally call it, in statistical terms, we call it the descriptive statistics. And this is the part I'll be talking on in the, next hour or so. Okay. So the first is study of the population. Then we define methods of collecting data from the population, and having collected the data, we have a sample, and then we study this sample. It's referred to as descriptive statistics. And finally, what we do is the statistical inference part. So having studied the sample, having got the sample in a well-organized manner by using the designs and the sample surveys, okay? Having studied this sample, we'll now need to go back and say something about the population. That is the goal of statistics, okay? Make inference about the population based on the sample that you have obtained from it, okay? That is the whole goal. So we have this in first three parts. Study the population. What are the characteristics of the population we want to look at? What are the characteristics of the sample that we have actually looked at, or we have actually got? And in between, we have collected the sample so that it represents the population properly, and then try to say something about the population based on the sample. So whenever you do, and because you're PhD students, you'll be looking at experimentation, so you should be careful on this, okay? Because if one doesn't relate to the other, then you get wrong answers, completely wrong answers. Okay, now let me come to just the descriptive parts, because I'll not be doing the other parts here. Okay, so the descriptive parts, first of all, what are the types of data that you get? And very often we have a confusion regarding data. There are two types of data. Maybe I'll just skip this. One is qualitative, the other is referred to as quantitative. So qualitative is categorical data like color, gender, or stages of disease, etc. So you can ask them opinions, etc. Things are qualitative. You ask them whether you like this or don't like this, you are in favor of this or not in favor of this, etc. These are referred to as qualitative. We just categorize them. We don't have a numerical value. Quantitative data, on the other hand, is numeric. Okay, and it can be two types. Either it's discrete or it can be continuous. Discrete, like how many goals there are in a football match, number of patients admitted in a hospital, number of cars that are passing through an intersection, traffic intersection. Okay, these are numbers, 1, 2, 3, 4, etc. Okay, it's not 1.5, 2.5, etc. Okay. On the other hand, data can be quantitative, data can be continuous. It takes all possible values in an interval, like height. Okay, there are some restrictions with the measuring instrument, but if you have if you look at temperature, for instance, you can talk about temperatures of, we generally talk about today's 27 degrees or 28 degrees, etc. Okay? But those who want to be more precise can look at it as 27.5 degrees or 27.56 degrees and so on and so forth. So basically it takes all values between 27 and 28. Okay. Sometimes the measuring instrument does not allow us to measure all these values because there are limitations of this measuring instruments. But you know that height, weight, temperature can take all possible values. We just say its height is 5 feet 2 inches or 5 feet 3 inches, but it can be 2.5 inches, it can be 2.5 points, more than that, 2 and say 5 feet 2.5869 inches and things like that. Okay, so these are continuous scales, whereas you can't have 1.5 goals in a football match or number of patients. This has to be round figures, so these are discrete values. Okay, but more importantly, you need to be careful about what qualitative and quantitative data are, because usually in statistics, quantitative data are easier to handle because these are numbers, and numbers are generally easier to handle rather than groups. Okay. Now, we have types of scales again for qualitative and quantitative. And qualitative is, we have what is referred to as nominal scales, which are unordered categories, like say color, gender, religion, and things like that. Okay. Ordinal are ordered categories like grade, opinions, stages of disease, things like that. Okay, I'll just give an example. For example, these days marks are given in grades. And if you know that somebody has got a grade A as opposed to somebody who has got a grade C, then the person who's got grade A has done better than somebody who is in grade B, and this somebody in grade B has done better than somebody in grade C. So you know that there is an ordering of this. A is better than B, B is better than C, C is D. Okay. So we say this is ordinal data, ordered categories. When you look at opinions, for instance, okay, you ask a question. Maybe there's a political decision that has been made, and you are asking people whether they support this or do not support this. So you have 5 categories. I very vehemently oppose this. Then I have an opposition, but not so vehement, maybe. Then I'm indifferent to it. Then I support this, and I very strongly support this. So if you look at this, you know that there is an ordering. The person who is very supportive of this is very different from the person who is very strongly opposed to this. Okay, and the other 3 are somewhere in between. Okay, so you get an ordinal data. But if you look at color or gender, you cannot say red is red, blue, yellow, green. These are ordered. Okay, they just come. So you can say red, blue, green, or you can say green, blue, red in any order. And there is no given ordering for this. Similarly, for gender, for religion, etc., it doesn't have to come by an order. Okay? I have got something to ask you here. This is something I am always confused with. I myself am confused with this. Is color nominal or ordinal? Yes, any one of you? I have put it as nominal, but I have a feeling that it will be ordinal too. Is it color is ordinal or nominal?
Both can occur because color intensity can be graded, like shades of color. Uh,
Okay, you can, but what about
it is more
red, yellow, and
intense.
blue?
Uh, it
Within
is
blue, you can do the shade.
nominal. Red,
No, yes,
blue.
yes and no. Yes, if you just look at it, red, blue, yellow, green, it's nominal. But remember that we have this frequencies per colors. You have done this. Okay, you know the rainbows. Okay, in rainbows have a pattern. It's VIBGYOR so violet, then indigo, then blue, etc., etc. So it basically depends on the wavelengths or the frequencies. Okay, so it has an ordering if you go by the wavelengths or the frequencies. In general, when you go to buy something, we don't have an ordering for colors. Okay, so anybody who prefers red to blue is neither of them is closer to green. Okay, it's completely different groups. Okay. But if you go by scientific methods, yes, colors, if you go by frequencies or etc., you can put it in the ordinal scale as well. Okay. So you should be careful as to what is nominal and what is ordinal. Ordinal data is more like numerical data because it has an order. Like numerical data always has an order because 1 always comes before 2 and 2 always comes before 3. So that's always ordinal. So similarly, ordinal data is easier to handle because it's closer to numeric data than nominal data. Nominal data are very difficult to handle generally statistically. Okay? Inferring from them is difficult. Okay? Quantitative data, again, there are 2 types, interval and ratios. These are numbers, but one has interval has no well-defined origin. Ratio has a well-defined origin as well. Okay. For example, if you look at temperature, time, etc., these are interval scales, but not ratio. Okay. Height, test score, incomes are ratio scales. Okay. It has a well-defined 0. What do I mean by that? It's simple that, okay, a father and son. Father is of height 6 feet and the son is a young lad. He's of height 3 feet. Okay, what did he say? Father is twice as tall as the son. Would you say that? Son is half the height of their father, right? A person has an income of 10,000 rupees. Another person has an income of 50,000 rupees. We say that the second person has a 5-fold more income than the first person. So we can say that. Okay. Now let's look at this. In January, the temperature in Calcutta goes down to around 15 degrees. In summer, it's around 30 degrees. Is it twice as hot? Yes. Do you call it twice as hot?
Students, please interact.
Okay, you're free to answer. Just. Okay. We wouldn't say it's twice as hot because the 0 is not. 0 is a temperature. So you see, in case of heights, in case of incomes, the 0 is defined. Okay, 0 means no height or no income, etc. And we have a point from which you move forward. But in case of temperature, 0 temperature is a temperature itself. It defines a given temperature. And hence, we cannot actually define ratios based on this interval scale. So we cannot say twice as hot. Okay, 8 o'clock is twice the time of 4 o'clock. We cannot say those things because the 0 in this case is not defined. Okay? So these are some types of scales that you'll be looking at. And data can be frequency or non-frequency data. Non-frequency means single observations corresponding to a given space or time. Okay? Frequency would be a number of occurrences of a particular category or value. Okay? And then you have continuous categorical. Maybe I'll just skip this, but if you look at non-frequency spatial data, it's something like this. I'm looking at table showing life expectancy at birth in the short countries. Okay, so life expectancy at birth in Afghanistan is 44.6 years, so they don't live very long because of the war or whatever the reasons are. You can see that it's very high in Sri Lanka, it's 74.4, in Maldives it's 72.3, etc. So this is non-frequency data. For each observation or for each country, I have got one single value. Okay, and very often we want to do a plot for this, and you know that what you generally do is a bar diagram. Usually this is spatial data, so we have bars which goes horizontal rather than vertical bars. Okay, so this is, so for each country we have a bar showing as to what the value for that country is like. Okay? Similarly, we can have a non-frequency time series data. So it's over time. So the life expectancy in India in 1980 was 55.35. It has improved over the time, and then in 2015 it's 16.35. Okay, so in this case, again, non-frequency, for each year you have a single value, and you can plot these values. So this is how the bar diagram would look like. Usually in this case you'll be having vertical bars. Okay, so this is referred to as non-frequency, and you can have other diagrams. In this, in case of time series, you can just join the top of the bars and you can get a curve for this, etc. So this is how you actually exhibit the data. The first thing that you always do in descriptive statistics is to exhibit the data, because it's very easy to comprehend when you have the data in a diagrammatic form. Okay. For frequency, we're looking at the number of pregnancies that a woman has. Okay, it's not the number of child; it's just the number of pregnancies, and you can see that the number of pregnancies for a given data set. There were 111 mothers who had no pregnancies. There were 135 mothers who had one pregnancy. So these are the frequencies. So number of pregnancies 0. There are 111 individuals corresponding to this. Number of pregnancies 1 is there are 135 individuals corresponding to this. So these are frequency type of data. And when you have frequency type of data, you can always, if there are too many numbers, so it's 0 to 11, too many classes to do that. There are 12 classes to look at. So instead what we do is we can group them. So instead of looking at 0, 1, 2, all the numbers, we can look at number of pregnancies between 0 to 2, and that's the total frequency in this group. Then 3 to 5, there are 200, etc. And you can similarly, you see the difference between the first group and the second group is that in this case I'm looking at the blood pressure level. Okay, so the diastolic blood pressure. Diastolic blood pressure, unlike, so what is the difference between the previous one, this example, and this example? Any guess? You see, in this case, we have 0 to 2, 3 to 5, 6 to 8, and in this case, it's 0 to 10, 10 to 20, 20 to 30, 30 to 40, etc. And again, you have the second column giving you the frequency. But there is an inherent difference between these two examples. What is it? So
Yes,
in the
sir.
first,
Yes, sir. In first case, there is interval of 2.
okay. In
And
this
in
case, an
the
interval of
second
10.
case, yes, sir. Yes, sir.
Okay, but there is one other big difference. That difference is that the first case, in this case, these are discrete data. It takes very specific values, 0, 1, 2, 3, 4, etc. Okay, so if I want, I do not make the classes here. I can just keep this table here, or I can make the classes here. Even if I make the class here, so 3 to 5 means it's only 3, 4, and 5. It doesn't mean 3.5, 4.5, etc. Okay, so this, mind you, is discrete data which I have put in a class. In this case, it's basically a continuous data. So a blood pressure can be anything like 83.5 or 90.2. Okay, so it can be, it just depends on how good the instrument is. Okay, so if you look at the 80 to 90 class, it can take all possible values within this class. 80, 81, 82, yes, fine, but also 80.5, 83.27, things like that. Okay, so this second table basically is for continuous data, and for continuous data you can only have classes. For discrete data you can have classes if you want, but you may not have classes. You can have specific values and the frequencies corresponding to this. Okay, but for continuous case, because if you have 500 individuals, each individual can have a different value. Therefore, it becomes impossible to put them into class, into frequencies. Okay, So in that case, what you do is you have groups. You make groups like 0 to 10, 10 to 20, and then see how many falls in this group, 0 to 10. Okay? So that is basically the difference between how you actually look at discrete data and how you look at continuous data. And when you have done this, what you do is you do a histogram. Okay? Histogram is just plotting this data. It's primarily for continuous data. For discrete data, it will be just column bars. For each number 0, 1, 2, 3, you have a different column, and you look at these columns. But in this case, the columns are connected, and you get to what is referred to as histogram. Okay. I think this, or you can do what is referred to as a frequency polygon. This is again based on continuous data. I think you know this thing, so I'll be just going very fast with this. But just before I end with this, diagrammatic representation is something that you should always be doing because it gives a very clear idea of what the data structure is like. Okay? You get a very good insight into the data when you do it. For example, if you look at this histogram here, you know that the maximum frequencies are at between 60 to 80, and then it falls off rapidly on both sides. Okay, so these are information. This gives you very quick information, and visually, if you are exhibiting this for people who do not understand your experiments, it's very easy to comprehend what you are doing by looking at them visually. Okay, so diagrammatic representations are something that we always do at the very beginning to get a good understanding of the data itself. Okay, then we come to measures, and the first measure that we look at is measures of central tendency. Okay? What are central tendencies? Central tendency gives an idea of the value around which the observations are clustered. Okay? And I'll explain this. So that these are standard measures. It's the arithmetic. It's called the mean. We call it the arithmetic mean. Then we have the geometric mean, harmonic mean, median, and the mode. I've colored two of them. The mean and the median. These are the two that you mostly use. So as I said, that there are various ways. Sometimes you do use the mode. Okay. Mode is something which has the maximum frequency. Okay? For example, if you go back to this example, you can see that the 70 to 80 group has the maximum. This group has the maximum frequency, and we call this the modal group. If you go back to the previous this one, and you see that the maximum frequency is at 1, so we say the mode is 1. That is the maximum number of mothers. Actually, the number of pregnancies is 1 for the maximum females. Okay. Okay, so these are referred to as a mode, but mode is not very well used because it gives a very good idea, but not a very comprehensive idea for the data. Okay? So what we generally look at is either the mean or the median. Median, or any idea what the mean and the median are? In general parlance, when you talk about average, we always think in terms of the mean. And as I said, in statistical language, you call it the arithmetic mean, but we'll always call it the mean otherwise, or even the simpler term of average. Okay, so it's the average that we will be looking at. So how do you do the average? I've got a math, as I said, I'll do some mathematical notations here, but you don't need to look at this last time. You just look at this. So usually it's defined by x bar. This is a notation that we write. Okay, and this average is just the sum of the values divided by n. Okay, so that is what we mean by average. Just take everyone's value, total it up, and divide it by n. Okay, it's like it's equally distributed value. Something, it's like, let me give you an example. You go for a picnic, okay, and everyone brings some food for the picnic. Okay, so suppose there are 10 of you. Okay, everyone brings some food, and some brings more, some brings somewhat less, etc. So in a picnic, okay, we want to enjoy, everyone wants to have the same thing. Okay. What do you do generally? What did you do in that case? You'll mix this whole thing up, right? You'll pull up the whole, all the food that you have and then divide this equally among yourselves. Okay? So all 10 of you will be getting the same amount of food, although some of you may have brought a little bit more, some of you may have brought a little bit less. You pull them up, that is sum the whole lot, okay? That's the total of all the food that you get, and you divide it equally among yourselves. What you get individually is the mean value. Okay, that is what is meant by mean. It's the equally distributed value. Okay, so technically, mathematically, you can write it as summation of x1, x2, xn divided by n, but actually it means that you are giving to each individual the same value. That value is referred to as a mean value. And obviously, the mean value will be somewhere in the center, right? Some brings more, some brings less, and when you average this out, the value will be somewhere in the center. It's like suppose in a class, okay, students get marks like, there are 3 students getting marks like say 20, 80, and 60. So we talk about what is the average mark. It will be 80 plus 20 plus 60, that is 160 divided by 3. It will be something like 53 point something, okay? So that is basically a representative mark which actually represents the group. It may be a very wide group, but the representative value would be somewhere in the center. It's between 20 and 80, somewhere in the center. Okay? And we say that it's a representative value. Okay? As opposed to this, we have what is referred to as the median. Median is referred to as the middlemost value when you have arranged the observations in ascending or descending order. So you have the observations, say the numbers 1, 5, 7, etc. So you arrange them 1 first, then 2, 3, etc. You arrange the numbers in increasing order. And if there are 100 numbers, you look at the 50th number or the 51st number, and this number gives you the median. Okay, so you make an arrangement of the numbers in order, and then you take the middlemost of these numbers. Okay? So this is the mathematical definition of it. Median is the middlemost value, okay, so once this has been arranged. So why do you look at the median at times rather than at the mean? Any idea? You have done the mean and median, okay? Can you tell me the difference? Yes? Yes, you know mean and median.
What happened?
Have you done this? I want to know if you have done median, because I'll not be dwelling much time on this, okay?
তোমরা মিন মিডিয়ান মোড পড়াশোনা করেছো না করনি? সৃজা একা পড়েছে, আর কেউ পড়নি?
Yes, ma'am.
Okay, yeah.
I have read it.
তাহলে
can you tell me? Okay, don't feel shy. Just tell me what. Can you tell me when do you use the mean and when you use the median? Okay, maybe I'll give you an example. Okay, in your class you have taken a test. 5 of you are in a class and you have taken a test, and the test scores are. Okay, I'll keep it simple. Suppose if the test scores are 90, 91, 93, 94. Okay, 4 scores. 90, 91, 93, 94, and one of the other students, the last student, actually has got a score of 20. Okay, and you want to find the mean of this. Guess what the mean is going to be like? Can you guess what the mean is going to be like? Mean is going to be something like 70 odd. Okay. Now, if you are not the 5th student, if you are the first 4 student, would you like that your class be represented by a score of 70 rather than 90? because all of you have got scores more than 90. Okay, except for one student. And what does that student do? Because if we add up all these numbers and then divide by 5, this is going to pull down the whole value. Okay? So you would not like one student to actually bring down the average marks. So in this case, instead of looking at the mean, what you'd be preferring to look at would be the median. Because if you arrange the numbers, 20 is the minimum, then 90 is the next, 91 is the third marks, 93 is the fourth, and 94 is the fifth. So third mark is 91, the median would be 91, whereas the mean would be somewhere in the 70s. So obviously you'd prefer to look at the median in this case rather than the mean. So what is the moral of the story? If you have outlying values, values which are very far away, actually the mean is affected by all the numbers, all the values. So if you have some values which are very far away, they would pull the mean towards themselves. Okay? So in that case, if you have outliers, you would not prefer to look at the mean, because the mean might not be representative. One bad value or one very good value actually makes a huge lot of change if you look at the mean. But if you look at the median, it does not generally influence the median. So if you have outlying values, you'd rather be looking at the median rather than the mean. Okay? That is one place. So we call median more robust in the sense that it is not affected by outlying values. Okay? That's the only time we'll be using the median. There is one other time when you have groups, like the groups I had formed before. If you are looking at these groups, and suppose, I just go back very quickly to this. Suppose the last group in this case is 120 to 130, but nobody knew that, okay, blood pressure can be higher than that. So one said that, okay, we'll put the last group as 120 onwards. Okay, rather than 120 to 130, we just put it as 120 onwards. In this case, we have an open class interval. And in that case, if you'll know that it will be very difficult to calculate the mean for that if you have open class intervals. So if you have open class intervals, again, you go back for the median. You can calculate the median. It's easy to look at the median. You know the formulas for this, so I'll not go into those. But if you have open class intervals, you'll be going for the median rather than the mean. So, but more importantly, you'll be going for median if you have outlying values particularly, okay? So if you have outlying values, the mean doesn't really work and you'll be going for the median, okay? I'll not go into the mathematical formulas, so these are the comparisons. So mean depends on all values and therefore is less robust. Median is, but one good advantage of the mean is that if you have different groups, so I have mean heights of Bengalis, I have mean heights of Punjabis, it's very easy to combine the two groups if you have the mean heights of these two groups. But if you have to have a median heights of the Bengalis and the median heights of the Punjabis, combining these two groups, you'll have to recalculate the whole thing from scratch all over again. Okay? So using the mean mathematically is much more easier than using the median. Okay? But then if you have outliers, obviously the median is the only way you should be going. The next part of it is, after the mean, we look at what is referred as the dispersion. And dispersion is referred as the spread of the data around the central value or the central tendency. You have the measures like range, mean deviation, variance or standard deviation, quartile deviation, and something called relative dispersion or coefficient of variation. Range, you know, is maximum value minus the minimum value. Okay? So, okay, in a class, I'll give you some examples. Okay? In a class, there are, okay, I'm not looking at the class, I'm just looking at one student or two students who are taking exams in two different papers, okay? And in paper A, and B, the first student has got marks like 0 and 100. Okay. In the other student have got marks like 40 and 60. Okay. What is the average mark of the first student? The mean marks of the first student? He has got marks of 0 and 100. So maybe 100 in mathematics and 0 in statistics. Other student has got marks of 60 in mathematics and 14 statistics. So what did you say about the students? Yes? What about the mean marks?
The mean
Both
marks of both are same.
So both are same, so you'll say that both the students are similar?
No, sir.
No. Yes, so the mean doesn't tell you everything, okay? So mean just tells you where it is centered. But what is the spread around the center? That's what the dispersion actually measures. In the first case, the spread is much wider. In the second case, the spread is. So the second student is basically probably more studious and does all the studies properly. The first student only cares about mathematics, doesn't care about the other subject, etc. Okay? So how do I measure this? One way of looking at it is to look at the range. For the first student is 100 minus 0, the range is 100. For the second students is 60 minus 40, so the range is 20. So for the second student, his marks are more clustered around the mean value. So the spread is much less, it's more clustered in the sense, okay? For the first student, it's much more dispersed, it's a huge spread, and we say that it has a very high range in this case, okay? The other way of looking at it is to look at the standard deviation, okay? Because very often the range only depends on the maximum and the minimum, and it doesn't give us a very good idea as to how the spread is, because I'm just looking at two values here. If you have more than two values, it may be that most of the values are at 100 and one value is at 0, and the spread range would not be able to capture this, because range would still be 100 minus 0. Okay? So the range doesn't depend on all the values and hence is not very well used. Gives you a very quick idea of what the spread is like. Okay? To look at the spread, we generally look at the variance. Okay? And the variance is a formula like this. So I'll not go into the formula for this. It's going to be non-negative. But it's something like we take the deviation of all values from the mean value. Okay? So for the first student, the mean is 50, his score is 100, so 100 minus 50, square that, and 0 minus 50, square that, okay? Sum this, and then you divide it by 2, okay, because there are two values. So 50 square plus 50 square divided by 2, and that is going to be 50 square. So 50 square is 2,500. It's a huge value. The variance is going to be 2,500. For the second student, it's 60 minus 50, which is 10. So 10 square plus 40 minus 60, which is minus 10. Again, if you square it, it becomes 10 square. So 10 square plus 10 square, which is by 2, which is 10 square. In this case, it's only 100. So you can see that the variance for the second student is only 100 compared to the variance for the first student, which is 2,500. Okay? And you know that the marks of the second student is much closer around the mean than the marks of the second student or the first student. The first student has a much wider range or wider variation than the first. So the variance actually gives us the clustering around the mean. The smaller the variance, the more closely clustered the values are. The larger the variance, the more dispersed they are. Okay? And you can see that if the marks becomes equal to the mean, or everyone gets equal to the mean, so everyone gets 50 out of 50. So what is the variance? The variance becomes 0 because everything is centered at the mean now. There is no variation from the mean. Okay? So variance can be 0 only when all the values are centered at the mean. So everybody gets the mean value. So everybody gets the same score the same score becomes the mean score, and there is no variation from the mean score. Okay, so that's the lower limit. The upper limit can be up to infinity, so it can be very large. The more dispersed it becomes, the larger becomes the variance value. Okay? The square root of the variance is referred to as the standard deviation. Standard deviations and variance are the same thing, just two ways of looking at the same thing. The reason variance is the something we calculate much more easily, and then we actually come from the variance by taking the square root. You will ask me, why do I need to take the square root? Because when you look at numbers, okay, suppose I'm looking at heights, then when you say it's the heights are so much, so and so feet, okay, or in centimeters maybe, okay, then the average height is also in centimeters. So you say that the average height is 167 centimeters, or maybe 5 feet 6 inches. You just don't say 5, 6, etc. Okay, it has to have a unit. Okay, so it has the same unit as the numbers. Similarly, the variance also has an unit, but since I'm squaring the numbers, you'll be saying centimeter squares. But if you talk about the standard deviation, it comes back into the same unit as the original numbers of the mean. So standard deviation is in centimeters, variance would be in centimeters square. That's the reason why we take the square root very often, but almost synonymously you can go from standard deviation to variance. Okay, so in either case you can be using the standard deviation or the variance. Relative dispersion is called the coefficient of variation is a relative dispersion. If the measures are different, very often we use this, but maybe I'll be running short of time, so I'll skip this slide here. Okay. There are two other things that we look at when we look at data. One is called the skewness, which gives the asymmetry of a distribution, and kurtosis, which gives the pickedness of a distribution. So how sharply picket, you see at the histogram was symmetric in the sense that it was falling off on both sides. But if you look at income, for instance, income distribution is not symmetric. There are more people with lower income than with higher income. So there will be more frequencies on the lower side than on the higher side. Okay, we say that it's skewed. It's skewed, positively skewed in the sense that the higher values are have less frequencies, and the lower values have more frequencies. It could even be negatively skewed the other way around, etc. So skewness gives us the asymmetry of the distribution. Kurtosis is how sharp the peak is. The sharper the peak is, we call it leptokartic. And then we have mesokartic, or it can be like a plateau, it can be flat topped, which is referred to as a platykartic distribution. So this gives us the characteristics of the sample values of observations. Okay. So first thing we look at is the central tendency, then we look at the dispersion, then we look at skewness and kurtosis. These characterizes the data. Okay, so these are different ways of, because you have 1000 observations. The problem is we cannot look at 1000 observations. We need to synthesize this, because if I ask you, there are 1000 individuals whose heights are measured. If I ask you something about the heights, and if you start reading out 1000 values, I will not understand. Okay, so for me to understand anything, you will have to give me some figures. The first figure that you give me would be the mean or the median. Okay, what is the central value against which all the other values lie? First you give me that. The second you give me would be how dispersed are these values around the central value. That it will be given by the range of the standard deviation or any other measures that I mentioned here. Next, is it skewed in the sense that are the values lying on one side of the mean mostly, and there are fewer values on the other side? That will give you skewness. And the kurtosis will tell you how sharp or how many values are around the mean, and how does it fall off on either side of the mean. If it falls up too sharply, we have a leptokartic distribution. If it's more flat, that is, all possible values are. So it can be a class having marks from 0 to 100. It can be that each group 0 to 10, 10 to 20 have an equal number of students. It's absolutely flat. Each of the groups have the same number of students. That's a flat distribution. But if you find that most students have scored between 40 to 60 and less as you go away from 50, okay, on either side. So very few at around 100, very few around 0. Then we have a very sharp distribution around 50. So kurtosis gives you a measure of this. So these are characteristics that you look at. So I think this part I'll stop here. We have what is referred to as a box plot, and this gives us all the characteristics, but maybe I'll skip this because the main focus of our study was to look at bivariate data, and maybe I'll come to that in a moment. So firstly, whenever you are given a variable, say you are looking at height, etc., you do its individual characterizations. As I said, mentioned, these are the 4 characterizations that we look at. But then we sometimes need to go beyond that. So often we may be interested in studying relationship between 2 or more variables. So I'm not just looking at height, I'm looking at both height and how is it related to, or how is weight related to height. So I'm looking at height and weight. I'm looking at blood pressure levels, blood sugar levels, cholesterol levels, and in this case, I can look at each of them separately as before. So I can look at X blood pressure levels, do its mean variance, do its skewness, kurtosis, do everything on this. I can similarly do the same things on blood sugar level, okay? Or maybe on the cholesterol levels, okay? But what now I am interested in is to see if there is a relation between the blood pressure level and the blood sugar level. If there is a relation between sugar levels and cholesterol levels, okay? So now I want to find out the relationship between different variables. Again, I can do the studies for individual variables as before, that I've done in the first part, individually for each of these variables. But my interest now is to know how these variables are related to each other. Okay? So separate studies are possible, univariate studies. Focus now goes to relationship between these variables. Okay? And I'll start with bivariate data. Multivariate data is if you have several variables. I just stick to 2 variables. So multivariate data, as I said, that you have all a large number of variables. Bivariate data would just be 2 variables. And it's very important because this is something that very often you go wrong with when you collect data. What is bivariate data? Bivariate data is observations which are naturally paired. That means observations that come from the same unit. Okay, let me give you some examples. For example, okay, maybe before I go with the examples here, I'll ask you these questions here. Okay? So get ready with your microphone. Maybe the next questions I'll ask you. Okay. If I'm looking at heights and weights, and I have a feeling that, okay, weight should depend on height. The greater the height, the possibility of weight would be more. Okay. And I want to do a study on this. So what I do is I go to 10 individuals, collect their heights, and I go to 10 individuals and collect their weights, and then try and compare this two. Am I doing the right thing? Yes. Now put your microphones on and answer me. Am I doing the right thing? I go to 10 individuals, get their heights. I go to another 10 individuals, get their weights. Am I doing the right thing? Yes? Okay, I need an answer from you. Is it right?
They are not related.
They are not related. So I have to measure the height and weight of the same person. Okay, so I can't go to 10 different persons, heights for 10 different persons and height for 10 completely different other persons. So it has to come from the same, so it has to be paired. In this case, it's very obvious, okay? But let me put it this way. I am looking at this. heights of brothers and heights of sisters, these are bivariate, but height of n men and heights of n women, this is not bivariate. Okay? So you just can't collect data separately, just look at what I'm interested in, how are male-female heights related. So I'm saying that male heights are, on the average, males are 5 inches taller than females. I want to test this. So I collect data. I look at n men and n females, okay? Now I can't pair them, mind you. If I want to pair them, then it has to come from the same unit. Family can be a unit. So it can be the husbands and the wives' heights, because very often they may be related, okay? But it can be brothers and sisters, but they come from the same unit. But if I collect data from two completely separately without looking at a given unit, it's not bivariate data. So it has to be naturally paired, okay? You have the next question, I leave it to you. Pollution levels on 10 roadside trees and 10 forest trees. Okay, I want to look at pollution levels. So our pollution levels, so I look at 10 trees, look at the pollution levels at these trees and 10 forest trees, okay? They do not come from the same unit, okay? But if I want to measure the daytime and the nighttime pollutions, okay, I'll have to look at the same tree and look at what the pollution level on the tree was during the day and during the night. It has to come from the same unit. You have to be very careful at times that this can get mixed up. So you should be, when you look at correlation regression, the data must be naturally paired. It needs to come from the same unit. And once you do that, the first thing, as I said, is always you draw a plot, okay, diagrams. And this is a diagram for, I think, anyway, it's a glucose versus diastolic pressure, etc. So you do a scatter plot. One axis you have X, on the other axis you have Y, and the diagram generally gives you a fair idea as to what the relation between these two values are, okay? So the lie of the points will tell you what sort of a relation, or whether you have any relation. So when you do this, obviously you need to have the same unit, observations coming from X and Y coming from the same unit, and plot it on this bivariate scale here, okay? So this is referred to as a scatter plot, and this is the first thing that we start from. And then what we look at is the covariance. Covariance is, you see the formula is somewhat like the variance, except that instead of only X, we now have X and Y. And we look at, okay, I'll not go into the details, we look at the correlation, which gives us an idea of the linear relationship between X and Y, okay? It would have been nice if I could have shown this on a board, but these are the properties of correlation, because again, correlation is something I'm not going to do in details, okay? So correlation is unit free. That's the reason why you look at correlation. It's generally always between -1 and 1. And let me go back to the previous slide. Covariance and correlations are almost synonyms. The problem with covariance is that, unlike correlation, has two advantages. One is it is unit free. That means I talked about unit before, that when you look at mean and the variance, it has to be in the unit, centimeters, etc., whatever unit you are measuring. Covariance also depends on the unit. So if you are looking at heights and weights, covariance would be in terms of both kgs and centimeters. Okay, centimeter, kgs, etc. So that is a little cumbrous to look at. When I look at correlation, correlation will have no unit, because you are dividing the covariance by the standard deviation, and the units actually cancel. Okay. Again, covariance can be anything between -infinity and infinity. However, correlation is always between -1 and 1. Okay. Now, important thing is, if R is close to 1, then we say there is a high positive correlation. Okay. If R is close to -1, then we say it's a high negative correlation. And if R is close to 0, we say there is no correlation. Okay. Let me go back to the figure and let me try and say, if the values lie along this, so if x is increasing with y, or y is increasing with x, if the values lie along this, then we say that we have a positive correlation. One increases, the other also increases. If one increases, then the other decreases. So if x increases and y starts falling, so it goes like this. Okay, in that case, we say that this is negatively related. It's an inverse relationship. Mind you, negative relations can be very strong also. So what is a negative relation? Every day you go to the market, okay, and you see if the price of a commodity is increasing, you buy less of it. So the more the price, the less you buy. It's a negative relationship, right? So in this case, the correlation is going to be negative. Sometimes it happens that whatever happens to x, y remains the same. Okay, so it's something like this. So whatever x, y are going to be similar. So in that case, you have a zero correlation. And if you have a zero correlation, we say that y and x are not related to each other, and hence there is no point in studying the correlation between them. Okay. So correlation R value actually, and if you do a computer programs would always give you the R values, but you need to explain what is happening. So R equal to 1 or equal to -1 means that the two variables are very, very highly related. Both cases, even it's 1 or -1, they are very highly related. If it is +1, then this high relationship is in the positive direction. That means they are directly related in the sense that if one increases, the other is also going to increase. If it is a very high negative correlation, then they are again very strongly related, but in the reverse direction, which means that if one increases, the other is going to decrease. Okay, and if neither happens, then you have no correlation. Okay, that is the last case. Now there are various other correlations. Again, I'll be skipping these slides because you can look at rank correlations. So instead of looking at the original values, you can rank the values and do a calculation on them. Sometimes it's easier because if you look at grades, marks, etc., it's rather easier to rank the individuals rather than actually mark them. And hence, instead of looking at the original values, we look at the rank values and do the correlation. So I'll just leave the slides out, these two slides. I'll come to regression. That's the part I was supposed to be talking about. Now, when we look at two variables and we say that there is some correlation between the two variables, y and x, then the question arises as to, if I'm giving one variable, can I say something about the other variable? Because they are related, okay? So if I say that the more the height, the more the weight, then given the height, can I predict something about the weight? Because you see, when I'm measuring, I'm going on a survey, I'm trying to measure the heights and weights of individuals. I want the heights and weights of individuals. But if I go around collecting the sample, going house to house, it's easy to go with a measuring tape rather than with a weight machine. Okay, so I just want to measure the height and say something about the weight also based on the height. So it will be experimentally easier to do. Can I do that? For that, I need to build up what is referred to as a regression model. So in a regression model, we have what is referred to as a cause variable and what is referred to as an effect variable. Cause is a regressor. In this case, I'm taking a single regressor, x, and the effect variable is the response or the y variable. So x causes y. Okay, and you should be very careful as to how you set up the model, because you have to first define what is a cause variable and what is the response of the effect variable. As I was giving you the example, height is the cause and weight may be the effect of this. Is the converse true? Can I take weight as the cause variable and height as the effect variable. Yes? Do you get
No,
my
sir.
problem?
No.
No, you
No,
can't
sir,
do
they are
that. You
not
can't do
correlated.
that.
No. They can't be correlated.
No,
Height and width can't be correlated.
they
It
are
can.
correlated,
They
fine.
are
Correlation
correlated,
doesn't tell
but
you
we
the cause
cannot.
effect.
No.
You
We
cannot
have
do the other
Actually,
way
to
when
around
the
because, yes. So because
weight
you
can
see,
can't be
weight
effect
doesn't,
of
so
height.
can't define height, yes. So the more the
Yes.
weight, you cannot say the more the height. Okay, height doesn't depend on weight, it's the other way around. Okay, so weight is the dependent variable or the response variable. Height is the, so when you set up a regression model, you have to be very careful about the cause effect. Very often we forget this. Okay, we just talk about y-x, etc., and when you talk about y-x, it doesn't mean anything. Okay, so it has to be the dependent variable or the response, which is the y variable here, which is the effect, and you have to be very specific as to what causes this effect. Okay, so when you have defined all this, we have what is referred to as a linear model. We have y is equal to capital Y and plus small y, where capital Y is beta naught plus beta 1. I'm just going into the mathematical details of this a little bit. And therefore, small y, this is the last line. The last line is something that you know of. You write a regression model as yi is, maybe you write it as b. I'm using the Greek notation, beta naught plus beta 1 xi plus ey. Okay, ey is the error part. Okay, and capital Y, if I go back to this here, so what I say is that I have a line, I know that there is a specific relationship between height and weight. Okay, this relationship is given by, this is capital YI here, this is the weight, and if x is the height, then this is the weight. So suppose this is 5, this is 2, so I'll get the weight as 5 plus 2 times height. Okay, so you give me any height, I'll give you the exact weight. This is what statistics would tell you. Okay, so I have got a straight line passing through this, and this would be the straight line. But when you collect data, obviously, you'll not, given a height, you'll not find anyone with a height weight of WI. There would be some errors involved. Okay, maybe he has eaten more that day, his weight has gone up a little bit because he's eaten too much, etc. So there would be errors involved. And so when you observe this, it's not exactly the true value that you observe it with some amount of error which is given by EY. So your observed YI would be what the predicted value is, what you can predict from X, plus some errors. Okay, so again, I'll put it this way. If you bring me 10 individuals with exactly the same height xi, I will not get all of them having the same weight, because some will be more, some will be less. So some will have some positive error, some will have some negative error. Okay, so but the centering would be around this yi value. Okay, so yi is basically the average value. That's exactly what should have happened, but there will be some, because of unforeseen reasons, because of other reasons, there should be some other errors involved. Okay, so somebody may have thyroid problems, somebody may have other problems of putting on weight, etc. So some would be less, some would be more, and hence what we'll end up with is a model like this, where the first part, this part gives you the actual true value based on x, and this part gives you the error part. Okay, so it's a true value, true part, that part x, this part we say is the part explained by x, and this is the part which is unexplained by x, which is the error part. So weight is not defined only by height. There are other things, eating habits, etc., which you have not taken into account, which goes into the error part. Okay, the part which is explained by height would be this part. Are you clear on this? Because this is important as to how you set up the model. Okay, so define your cause and define the responses, etc. Okay, and maybe I just tell you what this epsilon again. This is something I've already talked about. This is the error part, and you get a regression line like this. So this is a glucose diastolic regression, and if I give you the glucose level, you can give me the diastolic. So this is, but this is measured without error. Okay. So beta naught gives us the intercept when x is 0. So if x value is 0, what would be the y value? That is given by this 57 here. One unit increase in x, what would be the increase in y? That is given by the value here. So for every unit beta 1, actually the coefficient here gives us the change in y for a unit change in x. Okay. So again, these are technical things. Maybe I'll just skip through this and go to multiple regression. In multiple regression, again, instead of one single cause variable, we have, say, several p cause variables. P can be any number. So you can have 5 cause variables, 10 cause variables. For example, if I'm looking at weight, height may be one of the variables, but you can look at eating habits as another variable. You can look at family history as another variable. So there can be several variables. Okay, amount of exercise done as another variable. So you can have 3, 4, 5 variables in the model. Okay, the part, this first part, this capital Y part, as before, is a part which is explained by all the variables together. And whatever remains unexplained is the error part. It might be that there are certain variables you do not look at. Okay, maybe the person, you do not look at the number of hours he sleeps. Somebody is sleeping for 20 hours a day, and then probably his weight goes up. You are not looking at that, and that part would actually would be going to the error part. So the things that you do not look at, everything goes into the variation caused by this will go into the error part. So you are interested in this part only, the yi part. Okay, that's the part you can explain through the x's. Okay, and again the betas reflect. So if I change 1 unit of this x, what is the effect? Keeping everything else fixed, just change x1 1 unit of this. What would be the effective change in y? That is given by this coefficient here. So coefficient gives the change in y for a unit change in that variable, keeping all the other variables fixed. Okay, and if all the other variables are 0, that is, if you are at the origin, then the intercept gives you the value of y. Okay, so that's how you interpret these things. Okay. So there will be several examples. Again, I think for the sake of time, I'll skip this. Before I go with the regression itself, I'll just define 2 things. One is if it is a multiple correlation. You have looked at it, it's called R-square, and this R-square value is between 0 and 1, etc. It's called the coefficient of determination also. Now, what R-square measures is basically how the dependent variable is related to the whole set of x variables. So you have 5 x variables. How do the 5 x variables correlate with the response variable or the y variable? Okay. Now, you know that correlation is between 2 variables. In this case, we have a problem. We have one variable y on one side. On the other side, I have 5 variables. So there is a way of doing this. It's called the multiple correlation coefficient. We take a combination of the x variables and then look at the correlation, etc. But correlation, multiple correlation is generally between 0 and 1. It's never negative. So if it is 0, what does it mean? It means that the x's together do not explain y. Okay. If it is 1, it means that the x's together very well explains y. So the closer it is to 1, the better is the regression model. Because if it is 0, x's does not explain y, means that all the betas are 0. That means on the right hand side, the x's does not matter. Whatever the x is, y is going to be whatever it feels like. Okay, so X does not influences the Y. Okay, so one other thing is when you look at correlation, it's negative and positive. In this case, I'm saying it's just going to be positive, no negative values. Why? Any guess? Okay, it's because negative values gives you the direction. So it's inversely related, means it's negative. If it is directly related, it means positive correlation. Okay. In this case, we don't have that because there are several variables on the right hand side. So x1, x2, x5, maybe 5 variables. And it may be that y is directly related to one variable. So if you're looking at height, if height increases, weight increases. Okay. If you're looking at the amount of food intake, if food intake increases, then again weight increases. So number of hours awake, if the number of hours you are not sleeping increases, then probably your weight is going to decrease. You don't have enough rest and your weight might be decreasing in this case. So with some variables it might be increasing, with some variables it might be decreasing. So when we look at multiple correlation coefficient, we don't talk of a direction. Again, remember the sign gives you the direction. The closer it is to -1 or 1, the magnitude actually gives you the strength of the relationship. In this case, we just look at the magnitude and not the direction. Okay? So sometimes what we have is a spurious correlation. You should be very careful on this. We are looking at the divorce rate in a country and the butter consumption. And these are the figures for the different years, 10 years. And somebody was, I don't know why, but somebody decided, okay, we'll calculate the correlation between these two. And the correlation came out to be 0.99. And you can see it's very close to 1. Okay, so we'll say that divorce rates are related to butter consumption. Yes? Any fallacy about this?
Because they are not
Would you agree
related.
with this?
No, sir.
But it's showing a correlation of, I didn't miscalculate, so it's 0.9925. Okay,
But we cannot
so what is
correlate the
happening?
things. The butter intake is not related to
Yes,
the
it's called nonsense or spurious
yeah, the
correlation.
spurious
Wh-
correlation.
Why is this happening? Is because, firstly, it doesn't uh, indicate causality, but more, the reason is that if you look at this graph here, you see that both are decreasing with time. So there is a third variable, time, with which both of them are related. Okay. So as time increases, both
Sir, can you please
decreases.
explain it
And since
again?
both decrease with time,
Sir,
this one, okay. You can see from this graph here, I plotted the, yes,
sir,
yes,
please can
is
you
this
please
part, I'm
explain it
repeating
again?
this, okay? This part, yes, I'm trying to, okay? So you have this two over the years and you find a very high correlation. Then you see that if you plot this against time, both are decreasing with time. Okay, so both are related with time. So as time increases, both the divorce rate and the consumption of butter decreases. So what time does is actually spuriously correlates the two. Both are related because both are related to time and hence get correlated through time. You get the point? Time being a third latent variable, which basically makes these two correlated because both are decreasing with time, and since they are very closely related to time, they become closely related among themselves also. But if we eliminate time from them, then these two will be, you'll find that there is no correlation between them. Okay, so what we do is, what we look at is referred to as partial correlation. Partial correlation is the correlation between two variables, eliminating the effect of any other variable. Okay, so it's like it happens between people also. Two people, you see very often, okay, maybe I'll take a negative view of this, okay? Uh, you and your friend, okay, and you are very closely related. Okay? And then somebody plays a prank on you, comes and tells you something about your friend, which is negative, and goes and tells your friend the same thing. And if you listen to this person, you have a misunderstanding with your friend. Okay, so what this person basically is doing is influencing both of you, and you get a wrong influence between yourselves because you're both listening to this person. Okay, remove this person, and then you have a better understanding among yourselves. Okay, so this is what is referred to as partial correlation. Some other variable might play a role in making two other variables which are completely uncorrelated look like they are correlated. Okay, so when you look at partial correlations, total correlations, we do not eliminate other variables. But when we look at partial correlations, we look at we have to eliminate the effect of other variables and just look at the two variables with no influence from the other variables. Okay, and when you look at a regression setup, this is exactly what the individual betas will do. If the individual coefficient is 0, that means that x, irrespective of the other x's, does not explain y. Okay, so correlation, actually partial correlation is same thing as looking at individual betas being equal to 0. Okay. This is again the least square method. We try to minimize the errors. That is the EY. I've written epsilon I here anyway. So you are trying to minimize the errors. So you want to fit in the model so that the errors are minimized. You don't have to go into the mathematics. But again, as I said, you look at the R square. If the R square is high, then you know that the x's are a very good explanation of the y's, and you can use the regression model. If the R square is low, then these x's are not sufficient to explain y. It might be that some of the betas are positive and significant, in which case you say that, okay, these betas are good enough, these x's are good enough, but on the whole, you are missing out on some other variables which could have had an influence. So R square high, the higher the R square, the better is the model, or the better is the explanation from the set of x's that you have. The better explanation you can give for y. Okay. Then you have the usual test. I think this is something, first betas test, all the betas are 0 would mean that your R square is going to be high. So you look at first, if you have a high multiple correlation, then you know that the regression is good. And then you look at individual betas. If the individual betas comes out to be insignificant, then that means that variable does not have an influence on y. If it comes out to be significant, you can say that this variable I should be including. If this is insignificant, then can be taken to be 0, and I can drop the variable from the regression model. Okay. This is how a regression would look like. I've taken diastolic pressure as the y variable, glucose, BMI, and age as the positive variables here. These are the x variables, and you can see that the p-values, these are basically these are the standard, these are the estimates, sorry. These are the estimates, these are the standard errors, etc. But in this case, p-values will tell you whether this is significant. These two are significant, which means that BMI and age have an influence on diastolic pressure, but glucose does not have an, because this value is insignificant. So when you do the regression, this is insignificant. You can drop glucose from the regression model. So diastolic pressure primarily depends on BMI and age, but in this regression, the multiple R square is not very high, which means that diastolic pressure depends on BMI and age, but there are a lot of other factors which we have not included in the model, which gives us a good explanation for diastolic pressure. Okay. So I think it will take a lot of time to do this, but this is what you do in regression, and this is what statistics about. So in 2 hours, maybe, I don't know how much I've been able to do, but any questions? Yes. Yes. Any questions? No? No questions. Have you understood anything?
Yes, sir.
Yes, sir.
Yes. So everything is clear with all of you?
Yes, sir.
Okay then. Okay, then if you have any problems, you just let me know by mail or etc. But what I would like you to do is to not get too much bogged down with the formulas, etc. But try to understand what you're doing in this uh, when you do a statistical analysis. And I'd rather like you to set up the experiments properly, as I said at the very beginning, because if you don't have a good setup of the experiment, then the conclusions can be very erroneous. Okay, so you need to properly set them, you define your purpose properly, set it up properly, and then getting the results, you need to interpret the results properly, and then you are true. Okay, because the calculations, etc., I know you'll be doing it on computers, so there will be softwares doing this for you. Problem with softwares, they give you lots of results, and you'll have to decide on which result to keep and how to interpret these results, and which results you don't need actually and you can discount. Okay? Okay.
Hello,
Then?
sir.
Yes.
You have seen in the chat box, I suppose, that there is Shubhobroto Moitro with us. He is actually one of our resource person, and he is saying that, sir, this is Shubhobroto, not sure you can remember me. I am student of BR, sir, Mr. Bishwajit Roy. I went to you
Okay.
10 years ago to learn logistic regression. I am joining from Edmonton, Canada. You taught me, and I am fortunate enough to tell you that I am working as a respiratory epidemiologist in the University of Alberta. So privileged to see you again. So he was during the entire deliberation. So another fan following of yours, because I am always your fan, and now this person is also here.
Okay, great
And
to have you here with us. Okay. It's nice to have
yeah,
you, yes.
yes, sir.
It
And we
must be the
wish you
middle
all.
of the night now there, okay.
Yeah, and he took all the effort to listen to you, sir. And it has always been such a nice experience to have you with us, and you always being actually deliberate in giving us this consideration. And thank you
No,
so
that's
much
fine
for
with
your.
me as long as they understand something. As long as they understand these things, okay, it's fine for us, okay?
Yes, sir. Thank you so much.
Okay,
Thank you
and if
so
you have
much.
any problems, you can always come back to me, okay?
Sure, sir.
Okay
Sure,
then?
sir.
Okay,
Okay.
see you.
Okay, sir.
Okay.
Okay. Hello, students. Am I audible?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
আচ্ছা, তোমাদের দেখো, আমি একটা ইনফর্মালি একটা কথা বলতে চাইছি, যে কিছু ক্লাসেস আছে, এরপরে গৌরাঙ্গদেব চট্টোপাধ্যায় তোমাদের ক্লাস নেবেন, অনির্বাণ সরকার তোমাদের ক্লাস নেবেন, সেখানে তোমাদেরকে ডেটা অ্যানালিসিস হাতে কলমে শেখানো হবে, ইউজিং ভেরিয়াস কাইন্ডস অফ ফ্রি সফটওয়্যার। এগুলো অ্যাকচুয়ালি অনেক প্ল্যান করে শুধু তোমাদের বেনিফিট হবে এটা ভেবেই করেছি। তোমরা যদি এরকম বসে থাকো, মিডিয়ানের ভেতরে difference জানো না, এরকম যদি থাকো, this is actually very embarrassing for me, very embarrassing for me. আমার তো ফেলিয়ার বটেই, আর ইন জেনারেল আমাদের ডিপার্টমেন্টের একটা বিশাল বড় ফেলিয়ার। মানে আমি বুঝতে পারছি না যে মানে কি হলো যে সাধারণ প্রশ্নতে তোমরা ইন্টারাক্ট করতে আমার অ্যাকচুয়ালি আজকে খুব খারাপ লেগেছে। আমি চাইবো যে ভবিষ্যতে কিন্তু একটু মানে ইন্টারাক্ট করো, তাহলে খুব ভালো হয়। আর একটা জিনিস বলে রাখি যে আমি তোমাদের গ্রুপেও সেটা বলে দেবো, লাইব্রেরি সায়েন্সের কিছু কিছু লোকজন আছে যারা আমাদের এই ক্লাস নেবে। তোমরা একটু নিজের থেকে না সেই মেটেরিয়াল গুলো একটু চেয়ে নেবে। মানে আই ক্যানট অলওয়েজ স্পোক ইউ যে আহ, এটা চাও, এটা বলো, মানে এটা তোমাদের নিজের থেকে একটুখানি করে নেওয়া উচিত। বিকজ মানে আমাদের মানে মানে অল দ্য টিচার্স ফ্রম দ্য বিহাফ অফ দ্য ডিপার্টমেন্ট অফ হোম সায়েন্স, সবাইকার তরফ থেকে একটা কথাই বলছি, তোমাদের উদ্দেশ্য হচ্ছে so that you take home something. It's not যে শুধুই ক্লাস করলাম, হতেই পারে একটা দুটো ক্লাস একটু বোরিং হলো, সেটা হতেই পারে, আমি একদম বলছি। কিছু ক্লাসেস অ্যাকচুয়ালি বিলিভ মি আর একটু বড় হলে তোমরা বুঝতে পারবে যে এরা কি বড় মাপের লোকজন, এবং এরা আমাদের জন্য এই সময়টা দিয়েছে। উই আর অ্যাকচুয়ালি ভেরি লাকি, অ্যান্ড ইউ আর স্পেশালি লাকি এই জন্য বলছি যে এবারে এই লকডাউনের জন্য এবং এই কোভিড ক্রাইসিসের জন্য বিভিন্ন জায়গার থেকে আমরা লোকজনকে আনতে পেরেছি, যেটা কি সবসময় আহ, সম্ভব হতো না। মানে সেটা কিন্তু তোমরা মাথায় রাখো, অ্যান্ড ট্রাই টু মেক দ্য মোস্ট অফ ইট, আমার একটাই বক্তব্য। ঠিক আছে? ওকে, তো
Okay, ma'am. Yes,
ওকে
ma'am. Thank you, ma'am.
ওকে ওকে তাহলে
Okay.
আমরা আজকে আর আমাদের কোনো ক্লাস নেই, কালকে আবার আমরা দেখা করছি ওই সেম টাইম, সেম লিঙ্ক। ওকে
Okay, ma'am.
Okay, ma'am.
ওকে। ঠিক আছে, এটা লিখেছে I don't know anything. This is an emergency situation. ID. Please do not act as mediator. If you want to write to me, if Shantadi wants, she can also write to me. Shantadi লিখেছে Ubali, please inform Amit Ray to call the PG Board of Studies on Thursday at 4:30 PM or any other time after that. দেবমিতা 7টা বলেছে, এই বলছে না মানে কিছু বলার। আমার একটা অদ্ভুত এই ফোন হয়ে গেলে প্রবলেম হয়ে যায় কি বলতো, ফোন হয়ে গেলে প্রবলেম কি হয়ে যায় বলতো, যে আজকে যেটা সুগত সেনরায়ের আমার তো খুবই খারাপ আছে ডিপার্টমেন্টের সবকটা টিচারদের খুবই ডিফারেন্স আলাদা। আমি ফোন করছি। এইখানেই তো নিচেই বোধহয় বসেছিল দাদা।